Now let's talk about sampling distributions. A sampling distribution is the distribution of all possible values of a certain statistic when all possible samples of the same size are taken from the same population. We represent a sampling distribution just like we do any other probability distribution, sometimes in the format of a table or a probability histogram, or sometimes just by a formula. So again, sample means, sample variances, and sample proportions target the values of our population parameters. Now remember when we talked about probability distributions, we discussed how to find the expected value for a probability distribution. So notice here we have the expected value of x bar, in other words, the mean of the sample means. The expected value of x bar is just our population mean, mu. And when we look at the distribution of the sample means, it tends to be a normal distribution. For our next statistic, our variance, the expected value of the sample variance is just equal to the population variance. This distribution of the sample variances tends to be skewed to the right. And finally, our expected value for our sample proportion is just equal to the population proportion. And this one also tends to be a normal distribution. Here's an example of a sampling distribution. If we repeat this process, we roll a die 5 times, and we find the mean x bar, the variance s squared, and the proportion of odd numbers of each sample. What do we know about the behavior of all the sample means that we would get as we continue this process indefinitely? Well, here's what it would look like. Here's our procedure that we roll a die 5 times and we find the sample mean x bar. Now in this case, since we've got a fair die, all 6 outcomes are equally likely. So if we found the population mean, which would be the expected value of our original probability distribution, that would be 3.5. If we continue this process through 10,000 trials, here's one example of having done this. The mean turned out to be 3.49. And here's a graph of what the distribution looked like after the 10,000 trials. So notice it looks very much like a normal distribution. If we look at the variances for our 10,000 trials, our population variance for the original probability distribution would have been 2.9, and our sample variance turns out to be 2.88. And notice what this distribution looks like. It's skewed to the right. And finally, if we look at the proportions of odd numbers in each of our samples, since there are 3 odd numbers and 3 even numbers on the die, then our population proportion would be 0.5. For our 10,000 trials, the mean of our sample proportions turned out to be 0.5 also. And if we look at this distribution, it also looks like it's approximately normal. Here's another example. If we take a spinner that has 3 equal areas labeled 1, 2, and 3, we spin it twice, find the sample mean and the proportion of odd numbers of the results. Let's look at this and think about what possible samples we could get. For each spin there are 3 possibilities. So if we use the multiplication rule from probability, that means there are 9 possible samples. Here are the 9 possible samples that we could get. So here's spin 1 and spin 2. So here are our 9 samples. Then we can calculate the mean for each sample. And for this column, if we look at the proportion of odd numbers in the sample, for example, in this sample 1, 1, both numbers are odd. So our proportion is 2 out of 2, or 1. So our different possible proportions of odd numbers are either 1 or 0.5 or 0. If we look at the sampling distribution for the sample mean first, we would list all the different possible values for our sample mean. These are all the different values that came up from our 9 samples. The number of times each one occurred. So for example, the sample mean of 2 happened in 3 of those samples. Then since each of those samples was equally likely, then our probabilities are just 1/9 times the number of times that sample mean occurred. So here's our probability distribution for our sample mean. If we want to find the expected value for our sampling distribution, this is just like what we did in Chapter 5. Our expected value for this sampling distribution would be 2. Now if we think about the population mean for our original spinner, our 3 possible results were 1, 2, and 3. If we found the mean of those three, it would also be 2. The expected value for our sampling distribution and our population mean are the same value. Now if we look at the sampling distribution for the proportion of odd numbers, we're going to do the same thing. So here we have all the possible values of our sample proportion. So this is our random variable in this column, the number of times that each one occurred, so the frequency of each one of those values. And then again, since each of those 9 samples were equally likely, then our probabilities are just 1/9 times the frequency of each one of those sample proportions. In this case, the expected value of our sampling distribution turns out to be 2/3. And again, if we think about our original process using the spinner, 2 out of the 3 numbers were odd numbers. So the population mean for this would also be 2/3. Another thing that we're going to use this for is to find probabilities for sample means. The requirements to be able to do this are that our original random variable x has to have a distribution. It may or may not be a normal distribution with a mean mu and a standard deviation sigma, and our samples of size n are all simple random samples. They all have to have the same probability of being selected. The result, if we meet these requirements, is that as the sample size increases, the distribution of the sample mean becomes more and more like a normal distribution. Here are the 2 formulas that we're going to use for our sampling distribution for our sample means. The first one is really easy because the mean of our sample means is just equal to the population mean. The second one is a little bit harder to remember. This is that the standard deviation of our sample means is our original standard deviation divided by the square root of our sample size. And another name for this is the standard error of the mean. Practical rules that we use for this: if we have samples of size n larger than 30, then we can pretty much count on our distribution of our sample means being approximately normal. We get closer to a normal distribution as our sample size becomes larger. The second one is that if our original population is normally distributed, then it doesn't matter what the sample size is. It can be smaller than 30, and still the sample means will be normally distributed. Here's an example. An elevator is designed to carry up to 3,000 pounds. Assume the population of weights of men is normally distributed with a mean of 172 pounds and a standard deviation of 29 pounds. How likely is it that a group of 16 men will exceed the safe capacity weight of the elevator? Figure this out. If we take 3,000 and divide by 16, that's 187.5 pounds. So what we need to do is find the probability that the mean weight for a random sample of 16 men is greater than 187.5. Because if it is, then the total weight of the 16 men will exceed the 3,000 pounds. That's the elevator's safe capacity. So we have a distribution of sample means that's a normal distribution because our original distribution of men's weights was a normal distribution. Our mean is 172. It's the same as the mean of our original distribution. And our standard deviation for this distribution is our original standard deviation of 29 divided by the square root of our sample size. So it's 29 divided by the square root of 16. It comes out to be 7.25. So now we just have a normal distribution with a mean of 172 and a standard deviation of 7.25. So we want to find the z-score for the 187.5. Then we're going to draw the picture of our normal distribution, and here's our sample mean of 187.5. The corresponding z-score of 2.14, and if we look this up in a table, the area to the left of that is 0.9927. We subtract that from 1 and we would get 0.0073. What that means is the probability that our 16 randomly selected men will have a mean weight greater than 187.5 pounds is 0.0073. So the probability that a random sample of 16 men will exceed the safe capacity of the elevator is only 0.73%. One important difference here is that we are finding the probability that the sample mean is greater than 187.5. That's much different than finding the probability that one man weighs more than 187.5 pounds. If we wanted to find that probability, we would use the mean and the original standard deviation of 29 pounds. And in that case, we'd get a completely different answer of 0.2981. So the probability that one man weighs more than 187.5 pounds is almost 30%, where the probability that the sample mean for 16 men was more than 187.5 pounds was only 0.73%.